Light travels through time every time it moves through space. The moment light leaves a source, whether a lamp, a distant star, or the surface of the sun, it begins carrying information from a specific moment into the future. When we observe light, we are never seeing events as they are now, but as they were when that light began its journey. Welcome to AstraFlow. Here, science drifts quietly, and understanding comes without effort. If you'd like, you can share where you're listening from in the comments. Now let's begin. Light is often described as something immediate. It feels instant in daily life. When you turn on a light switch, the room brightens without any noticeable delay. When you look at an object in front of you, it seems present and current. But even in these familiar moments, light is already travelling through time. The delay is simply too small for human senses to notice. Still, it is there, quietly embedded in every act of seeing. To understand what happens when light travels through time, we begin by noticing a simple fact. Light does not move infinitely fast. It has a finite speed. This speed is the same everywhere in the universe, regardless of how fast the source or the observer is moving. In empty space, light travels at about 300,000 kilometers per second. That number is precise, stable, and deeply woven into the structure of physical law. Because light's speed is limited, distance immediately becomes connected to time. For every meter light travels, a tiny fraction of a second passes. For every kilometer, a little more time accumulates. This means that space cannot be separated from time when light is involved. Wherever light goes, time goes with it, quietly and inevitably. When light leaves an object, it carries information about that object at a specific moment. The colour of the surface, the temperature of a star, the movement of an atom, all of these details are encoded in the light at the moment it is emitted. From that instant onward, the information is no longer updated. It does not change as light moves forward, it simply travels. This is the first key idea. Light is not updated while in transit. It does not know what happens next to its source. Once emitted, it carries a frozen record of a moment that has already passed. When that light finally reaches an observer, the observer receives information from the past, even if that past is only a few billionths of a second away. In everyday life, this delay is extremely small. Light takes about 1 nanosecond to travel 30 centimeters. Your brain cannot resolve that difference. Your nervous system treats visual information as immediate, but physics does not ignore this delay. The universe always accounts for it, even when we do not. As distances increase, the delay becomes noticeable in principle, even if not in feeling. Light from the moon takes a little over 1 second to reach Earth. Light from the sun takes about 8 minutes. When we look at the sun, we are not seeing it as it is now, but as it was 8 minutes ago. The sun could, in theory, change suddenly, and we would not know until the light carrying that change arrives. This is not a special case. It is how all observation works. There is no universal now carried by light. There is only the moment of emission and the moment of detection, separated by time spent travelling through space. When light moves, it does not move through time the way humans experience time. Humans measure time by clocks, by biological processes, by cycles of motion. Light does not carry a clock with it. From the perspective of physics, light follows paths called null paths, where the passage of time along the light's own trajectory is zero. This does not mean light experiences anything. It means that time, as measured by clocks, does not advance along the path light takes. This creates a quiet contrast. For observers, light spends time travelling. For light itself, time does not pass in the usual sense. These two descriptions coexist without contradiction. They are different ways of describing the same physical process depending on the frame of reference used. What matters for us is that light connects moments across time. Every observation is a connection between two events. One event is the emission of light, the other is its detection. The time between them is fixed by distance and the speed of a light. Nothing can shorten that interval, nothing can bypass it. This makes light a natural messenger of time. It does not carry time deliberately, it simply cannot avoid doing so. The structure of the universe ensures that information must travel at finite speed. Light happens to be the fastest messenger available. As light travels, it does not age. It does not decay in the sense that information fades with time. In empty space, light maintains its fundamental properties. Its frequency, wavelength, and energy remain consistent unless affected by gravity or motion. Time passes for the universe around it, not for the light itself. This leads to a subtle but important idea. The past is not gone in the way we often imagine. It continues to exist in the form of light that is still travelling. Every moment that emits light sends part of itself forward indefinitely until that light is absorbed or scattered. The universe is filled with travelling records of past moments, moving silently through space. Most of this light never reaches us. It passes by unnoticed, but some of it does. Telescopes, cameras, eyes, and sensors intercept tiny fractions of this moving information. Each interception is an act of looking into the past, whether the past is near or distant. This is not something special reserved for astronomy. It happens every time you see an object across a room. The difference is only in scale. The principle is exactly the same. Distance sets the time delay. Light bridges that distance. In this way, light turns space into a timeline. Nearby space corresponds to the recent past. Distant space corresponds to deeper history. There is no sharp boundary where observation stops being present and starts being past. It is all past, layered smoothly by distance. At this stage, we are not yet dealing with extreme effects. We are not invoking relativity in its full depth. We are simply noticing the basic structure of observation itself. Light leaves, light travels, light arrives. Time passes for observers during that journey. This structure is stable. It does not depend on interpretation or philosophy. It is built into how the universe transmits information. Even if no one were watching, light would still travel. Time would still pass between emission and arrival, whether or not arrival ever occurs. As we move forward in this exploration, we will see how this simple framework expands. Motion changes how time is measured. Gravity alters how light moves. The expansion of space stretches light itself. But none of those layers replace this foundation. They rest on it. For now, it is enough to rest with this understanding. Light always comes from the past. Even when the delay is imperceptible, it is real. Every visual moment is already a memory by the time it reaches you. There is no urgency in this realization. It does not demand action. It simply describes how observation works. Light travels, time connects, information flows quietly from what was to what is seen. Let this idea settle without effort. Light moves steadily, carrying moments forward, linking events across time without pause or awareness. This motion continues whether we attend to it or not. Light has a speed, and that speed is not negotiable. It does not depend on how fast the source is moving or how the observer is travelling. In empty space, light always moves at the same fixed rate. This single fact quietly reshapes how time and space relate to one another. The speed of a light is not an abstract idea. It is measured, tested, and confirmed with extraordinary precision. Experiments using mirrors, rotating devices, atomic clocks, and spacecraft all arrive at the same result. Light in a vacuum travels at approximately 300,000 kilometers per second. This value is so stable that it is used to define fundamental units of measurement, including the meter itself. Because this speed is fixed, distance and time become inseparable when light is involved. If light travels for 1 second, it covers a specific distance. If it travels for 8 minutes, it covers the distance from the Sun to Earth. There is no way to change one without changing the other. Space becomes a measure of time, and time becomes a measure of space. In everyday thinking, distance feels like a static quantity. A room has a certain size, a road has a certain length. These measurements feel independent of time, but the moment light is involved, that separation disappears. To see something is to wait for light to arrive. The farther away the object is, the longer the wait, even if the waiting is too subtle to notice. This relationship is not limited to vision. Any information that travels at or below the speed of light is bound by the same constraint. Radio signals, infrared radiation, and even signals sent between spacecraft all obey this limit. The universe enforces a maximum speed for cause and effect. This limit has a calming consequence. Events are ordered. One event cannot influence another faster than light can travel between them. There is no instantaneous reach across space. Everything unfolds with built-in delays that preserve a consistent structure of cause and effect. When scientists first measured the speed of light, they expected it might behave like other speeds, adding or subtracting depending on motion. A fast-moving observer might expect light to appear slower or faster. But careful experiments showed something unexpected. All observers measure the same speed for light, regardless of how they move. This result forced a revision of how time itself is understood. If speed equals distance divided by time, and speed is fixed, then distance and time must adjust instead. They stretch or compress depending on motion, while light's speed remains constant. This is not a philosophical choice. It is a direct consequence of measurement. At this stage, we do not need the full structure of relativity. It is enough to recognize that light sets the pace of the universe. Nothing outruns it. Nothing bypasses it. It is the ultimate limiter of how quickly information can move. This means that when light travels through space, it also defines the flow of time between events. The interval between emission and detection is not arbitrary. It is fixed by distance and the speed of light. And all observers must agree on the sequence of events, even if they disagree on the exact durations. In practical terms, this is why looking farther away always means looking further back in time. There is no special mechanism involved. It is simply the consequence of light's finite speed. Space itself becomes a record of earlier moments. Even nearby objects participate in this structure. When you look across a large room, the light reaching your eyes left the object a tiny fraction of a second earlier. That delay is real, even though it has no practical impact on your actions. Physics counts it, even if perception ignores it. The speed of light also sets limits on coordination. Clocks separated by large distances cannot be synchronized instantly. Signals take time to travel. This is why timekeeping in space navigation, satellite systems and global communication must account for light travel time. Without this correction, systems drift out of alignment. These adjustments are not dramatic. They are quiet and precise. They reflect the steady, unchanging rule that light speed cannot be exceeded or bypassed. Every system that relies on timing must respect this rule, whether in deep space or close to Earth. As light moves forward, it does not slow down or speed up in response to passing time. It simply continues at its fixed rate. Time passes for observers, clocks tick, processes unfold, but light's motion remains unchanged. This stability gives light a special role. It becomes the reference against which all motion is measured. Fast or slow, near or far, all comparisons ultimately involve light as the standard. In this way, light's finite speed is not a limitation but a structure. It organizes events. It separates moments. It ensures that the universe unfolds in an orderly way with clear relationships between cause and effect. Nothing about this process requires intention or awareness. Light does not choose to limit speed. It simply follows the rules built into space-time itself. Those rules apply everywhere, without exception. As we let this idea settle, we can rest with a simple understanding. Light always takes time to travel. That time is fixed by distance. No observation escapes this delay, no matter how small or large the scale. This quiet constraint shapes everything we see, even when we do not notice it. The universe reveals itself only as fast as light can carry its information forward. When light travels only short distances, the time it takes is almost invisible to human awareness. Yet even in the closest, most familiar situations, light still arrives from the past. The difference is not one of kind, but of scale. When you look at an object in front of you, light leaves its surface and travels to your eyes. If the object is 1 meter away, that journey takes a little over 3 nanoseconds. Your nervous system cannot register such a delay. The signal processing in your brain smooths perception into a continuous present. Still, physics records the delay precisely. This means that nothing you see is happening in the exact moment you see it. Every visual experience is slightly delayed. The delay is so small that it does not affect interaction, prediction, or movement at human scales, but it remains a fundamental feature of observation. This becomes easier to notice when distances increase modestly. If you watch a distant object, such as a building across a valley, the light reaching you left that building microseconds earlier. Sound, by contrast, travels much more slowly. This is why distant events are often seen before they are heard. The difference between light and sound reveals that light's travel time is real, not theoretical. These small delays accumulate as distance grows. Light reflected from the moon takes about 1.25 seconds to reach Earth. When astronauts left footprints on the lunar surface, images of those moments arrived on Earth with a built-in delay. People on Earth watched events that had already happened more than a second earlier. The same principle applies to the Sun. Light from the Sun takes about 8 minutes to reach Earth. Every sunrise you see is already 8 minutes old. The energy warming the planet left the Sun long before you feel it. These examples remain within the scale of the solar system, where delays are still manageable. They do not disrupt daily rhythms, but they reveal the structure clearly. Space is never instantaneous. Light always takes time to cross it. In these nearby cases, the past we see is still connected closely to the present. 8 minutes is not a large separation. It does not feel like history. But the mechanism is the same as for the most distant galaxies. Only the duration changes. This continuity is important. There is no threshold where observation suddenly becomes historical. It is always historical. The difference is only how far back the record extends. Light does not distinguish between short and long journeys. It obeys the same laws everywhere. Whether travelling centimetres or light years, it carries information from the moment of emission forward without updating or refreshing. In practical life, we rely on this consistency. Technology such as lasers, fibre optics, and imaging systems depend on predictable light travel times. Engineers account for nanosecond delays when designing high-speed electronics. In these systems, even tiny differences matter. This reveals another quiet truth. The present as we experience it is a constructed approximation. Our brains integrate delayed signals from vision, hearing, and touch into a coherent experience. That experience feels immediate, but it is built from information that arrived at slightly different times. Light contributes to this integration by arriving faster than most other signals. It anchors perception, but it does not eliminate delay. It simply minimizes it. As we step slightly beyond everyday scale, this delay becomes easier to conceptualize. Watching the moon through a telescope, we are seeing it as it was just over a second ago. Watching the sun through specialized instruments, we are seeing conditions that no longer exist in the same configuration. These facts do not add drama, they add clarity. They show that time delay is not an exotic feature reserved for extreme physics. It is present in the most ordinary act of looking. Once light leaves a surface, the information it carries is fixed. If the source changes after emission, that change will only be known when new light carrying that update arrives. Until then, observers continue to receive the earlier version. This applies even at human scales. If an object moves suddenly, the light reflecting its new position takes time to reach you. The difference is too small to matter in daily life, but it is still real. By noticing these nearby examples, we build intuition without strain. Light does not cheat time, it does not compress it to zero. It respects distance everywhere. This understanding prepares us to move outward, where delays stretch from minutes to years and beyond. The rules do not change, only the scale does. For now, it is enough to remain with the familiar. Light from nearby objects already arrives from the past. The present we see is always slightly behind the present we occupy. This is not a problem to solve. It is simply the way observation works. Light moves steadily. Time accumulates quietly along the path between source and observer. As distance increases, something subtle happens to observation. It begins to feel less like witnessing an event and more like accessing a record. Light does not change its behavior, but our relationship to what it carries slowly shifts. When light travels farther, the time gap between emission and detection grows. A few nanoseconds become seconds, seconds become years, and years become millions of years. At each step, the light still obeys the same rules. It carries information forward at a fixed speed, unchanged in essence. This is where distance turns into history. A nearby object appears almost current because the delay is negligible. A distant object appears ancient because the delay is large. Nothing special happens at the boundary. There is no moment when light becomes historical. It simply continues travelling. In astronomy, this effect becomes unmistakable. When we observe a star that is 10 light years away, the light reaching us today left that star 10 years ago. If the star changed yesterday, we will not know until 9 years from now. The image we see is a snapshot of a past state preserved by the journey of light. This does not mean the star is frozen in time. It continues to evolve. Nuclear reactions proceed, matter moves, gravity shapes its structure. We are simply not receiving information about those changes yet. Light acts as a delayed messenger. At larger scales, this delay becomes the dominant feature of observation. Galaxies millions of light years away are seen as they were millions of years ago. The universe reveals itself not as a single moment, but as a layered sequence of moments spread across space. This layering is not an illusion. It is a direct consequence of light's finite speed. Every direction we look corresponds to a different time depth. Nearby regions show the recent past. Distant regions show deep history. The universe, in this sense, does not present itself all at once. It presents a collage of moments, each carried to us by light that left its source at a different time. Observation becomes an act of assembling these moments into understanding. This does not introduce uncertainty. On the contrary, it provides structure. Knowing the distance to an object allows us to know exactly how far back in time we are seeing. Distance becomes a timestamp. Astronomers rely on this relationship. By measuring how far away a galaxy is, they know how old the light they are receiving must be. This allows them to reconstruct sequences of cosmic change, even though they cannot observe those changes directly as they happen. In this way, light transforms the universe into a natural archive. It does not store information intentionally, it simply preserves it through motion. Every photon travelling through space carries a small piece of the universe's earlier state. Most of this information will never be collected. Light travels in all directions, only a tiny fraction intersects with detectors, but the information exists nonetheless, moving steadily outward from its source. This perspective removes the idea of a single, universal present. There is no moment in which all parts of the universe are observed as they are now. Each location has its own present. Observation connects us to different presents from the past. This is not a limitation of technology, even with perfect instruments. The delay imposed by light travel cannot be removed. No device can make distant events appear current. The delay is built into space-time itself. As distance increases, certainty does not fade. Instead, perspective shifts. We become observers of processes long underway. The universe does not rush to update us. It reveals itself at the pace light allows. There is a quiet stability in this. The past is not lost. It continues to travel through space, accessible wherever its light arrives. History is not abstract. It is physically present as radiation in motion. At this stage, it is enough to notice how smoothly this transition occurs. Near becomes far. Present becomes past. Light does not signal the change, it simply continues its journey. The idea can rest without strain. Distance stretches time, light carries moments forward. The universe unfolds not as a single frame, but as a sequence gently spread across space. Every journey of a light begins with an event. That event is the moment light is emitted. Whether it comes from an atom, a heated surface, or the core of a star, emission marks the point where information becomes mobile. At the smallest scale, light is emitted when energy changes form. An atom absorbs energy. Its electrons shift to higher energy states, and when they return to lower states, light is released. The wavelength of that light depends on the energy difference involved. This process is precise and repeatable. It happens the same way everywhere in the universe. At larger scales, the same principle holds. A hot object emits light because the motion of charged particles produces electromagnetic radiation. A star emits light because nuclear reactions in its core generate energy that moves outward and eventually escapes as radiation. In each case, light carries information about the physical conditions at the moment of emission. This moment is important because it fixes what the light will represent. Once emitted, the light no longer responds to changes at its source. If a star's surface cools or heats after emission, that change will only be reflected in light emitted later. Earlier light continues on unchanged. This gives emission a quiet finality. The state of the source at that instant is locked into the light. Time moves on at the source, but the light carries only what was true at the moment it left. Emission does not require awareness or intent. It is a natural consequence of physical processes. Matter interacts, energy moves. Light is released. The universe continuously generates light without pause. Once released, light immediately begins travelling outward at its fixed speed. There is no delay between emission and motion. Light does not linger. It departs as soon as it is created, following paths determined by the structure of space-time. From the perspective of the source, emission marks a loss. Energy leaves, information departs. The source cannot retrieve it. From the perspective of an observer, emission marks the beginning of a possible connection, one that may or may not ever be completed. This asymmetry is quiet but important. Emission happens regardless of whether detection occurs. Light does not require an observer. It does not aim itself. It spreads outward, indifferent to what it may encounter. As light moves away, it carries a snapshot of the source. That snapshot includes details such as temperature, composition, motion, and structure. Astronomers decode these details by analysing the light spectrum and intensity. The information is embedded in the light itself. Once emission occurs, the information is no longer local. It is distributed across space as light travels. The source continues to change, but earlier states remain represented by light already in transit. This is how the universe preserves its own past. It does not store it in memory. It sends it outward, encoded in radiation. Each moment produces a new wave of information that moves away from its origin. At human scales, this process is constant and unnoticed. Every surface around you emits and reflects light continuously. Each moment generates countless photons that carry information about that moment into the surrounding space. Most of this light never returns to the source. It disperses, absorbed by other surfaces or lost into the wider environment. But the principle remains. Every moment leaves a physical trace in the form of travelling light. This process does not accumulate in a single place. The past does not pile up, it spreads. The universe's history is not stored in a central archive. It is distributed throughout space as moving radiation. This understanding removes any sense of urgency from observation. There is no rush to capture light. If light reaches a detector, it brings the past with it. If it does not, the past still exists in motion elsewhere. As we move forward, we will consider what happens to light after emission as it travels through space and interacts with gravity, motion, and expansion. But the starting point remains the same. Light begins with a moment. That moment is not special by itself. It is one of countless events occurring continuously throughout the universe. But once light leaves, that moment becomes part of the universe's travelling history. Let this idea settle quietly. Emission fixes information. Light departs. Time continues at the source. The universe moves forward, carrying its earlier states outward in steady waves. Once light has been emitted, it enters space and begins its long passage. In regions where matter is sparse, light travels through what we call a vacuum. This is not an absolute emptiness, but a space largely free of particles that would interfere with light's motion. In these conditions, light follows the simplest possible path through space-time. In a vacuum, light moves in straight lines at its constant speed. It does not slow down due to time passing, and it does not change simply because it has travelled far. Distance does not tire light. Time does not wear it down. Its motion remains steady. From the perspective of observers, light takes time to cross space. Seconds, years, or billions of years may pass while light is in transit. During that interval, stars evolve, galaxies change shape, and planets form and disappear. Yet the light continues, unaffected by these changes unless it encounters something that alters its path. This creates a contrast between the passage of time in the universe and the journey of light itself. Time flows for matter, processes unfold. But along the path light takes, time does not accumulate in the usual way. In the language of physics, the interval experienced by light is zero. This does not mean light experiences anything. It means that clocks do not tick along the path light follows. This idea can feel abstract, but its consequences are simple. Light does not carry a sense of duration. It does not age. It does not become older the longer it travels. For light, the moment of emission and the moment of detection are not separated by time along its own path. For observers, however, the separation is real. Clocks measure it. Calendars mark it. This difference in description is not a contradiction. It reflects the fact that time depends on the path taken through space-time. While travelling through vacuum, light preserves its internal structure. Its frequency, polarization, and phase remain consistent unless influenced by motion or gravity. The information it carries stays intact. This stability allows light to function as a reliable messenger across vast distances. Signals sent from spacecraft travel for hours before reaching Earth, yet arrive with their information preserved. Light from distant galaxies travels for billions of years, yet still carries clear signatures of the atoms that emitted it. The emptiness of space plays a quiet role here. Without frequent interactions with matter, light is free to move without scattering or absorption. Most of the universe is empty enough to allow light to travel largely undisturbed. Occasionally, light does encounter particles, dust, or gas. These interactions can scatter or absorb light, altering its direction or removing it entirely. But in the vast stretches between galaxies, these encounters are rare. Light spends most of its journey in near-perfect freedom. As light travels, it does not keep track of how far it has gone. Distance is a measure used by observers, not by light. The universe provides a stage and light moves across it without reference to milestones or endpoints. This makes light's journey neutral. It does not seek a destination. It does not anticipate arrival. It simply follows the geometry of space-time until it is absorbed or detected. In this sense, light is a connector between moments rather than a traveller experiencing a journey. It links an emission event to a detection event, without anything in between that counts as internal experience. This perspective helps clarify what it means for light to travel through time. From our point of view, time stretches between emission and arrival. From the structure of space-time itself, that stretch belongs to the observers and the space light crosses, not to the light. As we look deeper into the universe, we rely on this stability. We trust that light reaching us today accurately represents conditions from long ago. Without this trust, observation would lose its grounding. For now, it is enough to recognize that light in empty space is unchanged by the passage of time around it. It carries information forward without aging, without awareness, and without deviation. The universe continues to change while light moves on, quietly linking distant moments through its steady motion. When we talk about light travelling through time, it can be tempting to imagine light as something that experiences a journey. But this is not how physics describes it. Light does not have an internal clock. It does not register duration. Along the path light follows, time does not pass in the way it does for material objects. This idea comes from how space-time is structured. For objects with mass, time advances as they move. Clocks tick, processes unfold. For light, the path it follows is different. It is a path where the measure of elapsed time is zero. This is not a statement about sensation or awareness. It is a statement about geometry. Because of this, light does not experience a before and after. The moment of emission and the moment of detection are not separated by time along light's own path. From the perspective built into the equations of physics, those two events are directly connected. For observers, this is not how it feels. We see light leave a source, then wait. Seconds pass, years pass. In that waiting, time clearly advances. The difference lies in perspective. Time belongs to observers and their clocks, not to light itself. This distinction helps clarify a common misunderstanding. Saying that light does not experience time does not mean that light arrives instantly from the observer's point of view. The delay is real. It is measured. It affects observation. It simply does not belong to the light's own path through space-time. This difference becomes important when we consider extreme speeds. As objects move faster and faster, time for those objects slows relative to stationary observers. This effect is small at everyday speeds and becomes noticeable only near the speed of light. For light itself, the limit is complete. Time does not advance along its path at all. We do not need to imagine what this is like. There is no inner perspective to reconstruct. Light does not observe its own journey. It does not accumulate moments. It simply connects two events in space-time. This helps remove unnecessary mystery. Light travelling for billions of years does not carry a sense of age. It does not become ancient. It arrives exactly as it left, unless altered by interactions along the way. For us, the arrival is meaningful because of the time that has passed elsewhere. Entire histories unfold while light is in transit. Civilizations rise and fall, stars form and die. The light remains unchanged, while the universe around it evolves. This contrast highlights why light is such a powerful tool for understanding time. It allows us to receive information from moments long gone, without that information being diluted by the passage of time itself. When we detect ancient light, we're not detecting something worn down by age. We're detecting a direct signal from an earlier state of the universe. The distance it travelled tells us how long ago that state existed, but the signal itself remains precise. This also explains why light can serve as a reference in physical theories. Because it does not carry its own time, it provides a stable framework for relating time measurements made by different observers. At this point, It is enough to rest with the idea that time does not belong to light in the way it belongs to matter. Light does not age, it does not wait, it does not accumulate duration. For observers, time continues to flow. We receive light after delays set by distance. We interpret those delays using clocks and calendars. Light simply arrives when it arrives. This quiet difference between observer time and light's path will become important as we introduce motion and gravity. For now, it offers a calm clarification. Light connects moments without experiencing the interval between them. To understand why light and time are linked so closely, we need a framework that treats them together. This framework is relativity. It does not add drama or complexity for its own sake. It simply describes how the measurements of space and time behave when light speed is fixed. Before relativity, time was treated as universal. It was assumed that all observers shared the same ticking clock, regardless of motion. Light was expected to behave like other moving things, adding or subtracting speed depending on the observer. Careful experiments showed this expectation was wrong. Relativity begins with a simple observation. The speed of light in a vacuum is the same for all observers. From this, everything else follows. If speed is fixed, then measurements of distance and time must adjust instead. This adjustment is not optional. It is enforced by the structure of space-time. Observers moving relative to one another will disagree about lengths and durations, but they will always agree on the speed of light. This does not mean reality becomes subjective. It means that space and time are not independent. They form a combined structure called space-time, where measurements depend on motion and position. Light sits at the center of this structure. Its paths define the boundaries of cause and effect. No signal can travel faster. No influence can arrive before light could. Relativity also formalizes the idea that light does not experience time. In the equations, the interval along a light path is 0. This is not a poetic statement. It is a mathematical property of space-time. For observers, this has clear consequences. Events that appear simultaneous to one observer may not be simultaneous to another if they are separated by distance and motion. Light's travel time sets the limits on how simultaneity can be defined. This does not disrupt everyday life. At human speeds and distances, these effects are too small to notice, but they become important in systems involving high speeds or large distances, such as satellites, particle accelerators, and astronomical observations. Relativity does not change the behavior of light, it explains it. Light continues to travel at its fixed speed. What changes is our understanding of how time and space respond to that fact. In this framework, time is not a background flowing independently. It is part of the structure that light moves through. The way time is measured depends on the observer's motion through space-time. This explains why different observers can measure different times between the same events without contradiction. The events themselves are fixed. The paths observers take through space-time differ. Light provides the reference that keeps these descriptions consistent. Because all observers agree on light speed, their measurements of time and space remain connected in a predictable way. At this stage, it is not necessary to work through equations or thought experiments. It is enough to recognize that relativity formalizes the relationship we have already observed. Light links space and time inseparably. This framework will help us understand how motion and gravity affect light's journey. But the core idea remains calm and simple. Light sets the structure. Time and space adjust around it. We can let this understanding settle without effort. Relativity is not a departure from common sense. It is an extension of careful measurement, grounded in how light actually behaves. Once motion enters the picture, the relationship between light and time becomes more apparent. Observers moving relative to one another do not measure time in exactly the same way, and light reveals this difference without ambiguity. Imagine two observers in motion relative to each other. each carrying a clock. When light travels between them, both observers will measure its speed as the same. To preserve that consistency, the time recorded by their clocks cannot be identical. One clock will tick slightly differently than the other depending on motion. This effect is known as time dilation. A clock moving relative to an observer runs more slowly than a clock at rest with that observer. The effect is small at everyday speeds and becomes noticeable only as speeds approach that of light. But the effect is real, measurable, and confirmed by experiment. Light plays a central role here. Because its speed cannot change, time must adjust instead. The faster an observer moves through space, the more slowly time passes for that observer relative to a stationary one. This is not a mechanical slowing. It is a structural feature of space-time. For light itself, this adjustment reaches an extreme. At the speed of light, time does not advance along the light's path. This does not mean light is a reference frame. It simply marks the limit where time ceases to accumulate along that trajectory. When observers measure light travelling toward them, the timing of its arrival depends on their motion. An observer moving toward a light source encounters the light sooner than one moving away. Yet both measure the same speed for the light when it arrives. The difference appears in how they measure time and distance, not in light's behaviour. This is why moving observers disagree about timing, but agree about causality. One event still precedes another. Light still arrives after it is emitted. The order of events remains consistent even when durations differ. These differences matter in precise systems. Satellites orbiting Earth move at high speeds and experience time slightly differently from clocks on the ground. Their systems must correct for this difference to maintain accurate positioning. Light signals exchanged between satellites and receivers reveal these timing shifts. In these cases, light acts as both messenger and referee. It carries information and enforces the rules that timing must obey. Motion cannot hide from light. Differences in time measurement become visible through light's travel. This does not introduce confusion. It introduces consistency. All observers, regardless of motion, can describe events using the same physical laws. Light ensures that these descriptions fit together without contradiction. As we let this idea settle, it becomes clear that motion does not disrupt light's role as a carrier of the past. It refines it. Time stretches or compresses depending on motion, but light still connects emission to detection reliably. The universe remains orderly. Motion alters perspective, not reality. Light continues its steady journey, revealing how time responds when observers move through space. Motion is not the only influence on how time behaves. Gravity also plays a role. Where gravity is stronger, time passes more slowly. Light moving through these regions reveals this effect in a quiet, measurable way. This connection comes from the way gravity shapes space-time. Massive objects do not merely attract other objects, they curve the space and time around them. This curvature affects how clocks tick and how light travels. Near a massive object such as a planet or a star, time runs slightly slower than it does far away from that mass. The difference is small near Earth, but becomes significant near very dense objects. This effect is not hypothetical. It has been measured using precise clocks placed at different heights above Earth's surface. Light responds to this curved space-time by changing its path and its timing. As light moves away from a gravitational field, its frequency shifts slightly. This shift reflects a difference in how time flows at the source compared to the observer. This phenomenon is known as gravitational time dilation. It does not mean gravity reaches out and slows light directly. Instead, gravity changes the structure of space-time, and light follows that structure. When light climbs out of a gravitational well, it loses energy in a specific way. Its wavelength stretches, and its frequency decreases. This change encodes information about the gravitational field it passed through. Observers can detect this change by comparing the light received to light emitted under different gravitational conditions. The differences are small but precise. They confirm that gravity affects time and light together. In this way, light becomes a probe of gravity. It carries not only information about its source, but also about the space-time it traversed. The journey itself leaves a measurable imprint. This effect is present everywhere. Even the weak gravity at Earth's surface causes time to pass slightly differently than it does at higher altitudes. Systems that rely on precise timing, such as navigation satellites, must account for this difference. Without correction, their signals would drift out of sync. At larger scales, gravity's influence becomes more pronounced. Light passing near stars, galaxies, or clusters follows curved paths. Time along those paths differs from time far away. Observations must account for these effects to remain accurate. This does not complicate light's role as a time messenger, it enriches it. Light still carries information from the past, but that information now includes details about gravitational environments encountered along the way. As we move deeper into regions of stronger gravity, these effects become more noticeable, but the underlying principle remains calm and consistent. Gravity shapes space-time. Light moves through that shape. Time responds accordingly. For now, it is enough to recognize that gravity and light are linked through time. Light traveling through gravity carries subtle signatures of how time flows in different regions of the universe. As gravity becomes stronger, its influence on light and time becomes easier to notice. Near very dense objects, the quiet effects described earlier grow more pronounced, yet they still follow the same physical rules. Nothing sudden happens. The changes increase smoothly as gravity intensifies. Dense stars, such as neutron stars, compress large amounts of mass into very small volumes. The curvature of space-time around them is steep. Clocks near their surfaces tick more slowly than clocks far away. Light emitted from these regions carries this difference outward as it travels. When that light reaches distant observers, its frequency appears reduced. The light has not aged or weakened in a conventional sense. Instead, the flow of time at the point of emission was slower relative to the observer. The light faithfully records that difference. Near black holes, this effect becomes extreme. Gravity there curves space-time so strongly that time near the event horizon slows dramatically compared to time far away. Light emitted close to this region struggles to escape. As it does, its wavelength stretches significantly. To a distant observer, light emitted near a black hole appears increasingly redshifted. It carries information from a region where time was passing much more slowly. This does not mean time stops. It means the comparison between clocks in different regions becomes very large. Light approaching a black hole from outside also follows curved paths. Its trajectory bends as space-time curves. This bending does not disrupt the information carried by the light. It alters where the light goes and how long it takes to reach an observer. In these extreme environments, light still travels at its constant speed locally. Even near a black hole, light does not slow down in its own frame. The changes we observe arise from how space-time itself is shaped by gravity. This distinction is important. Gravity does not act like a force dragging on light. It changes the geometry through which light moves. Light follows that geometry without resistance or effort. Despite the intensity of these effects, there is no breakdown of physical law. The same principles that apply near Earth apply near black holes. The differences lie only in scale and strength. Light escaping from regions of strong gravity carries precise information about those regions. By studying this light, scientists can infer properties of objects that cannot be observed directly. Time dilation, redshift, and light bending become tools for understanding the structure of space-time. These observations do not rely on speculation. They are grounded in measurement. Light arriving from near massive objects consistently matches predictions based on gravity's effect on time and space. As we let this settle, it becomes clear that even in the most extreme environments, light remains a steady messenger. It connects distant observers to regions where time flows differently, without confusion or distortion beyond what physics describes. The universe does not hide its structure. It reveals it through light, even when gravity is strong and time flows unevenly across space. When we step back from individual objects and look outward, light reveals something broader. The universe itself becomes a record of time. Every direction we observe corresponds to a different era, not because the universe is arranged that way intentionally, but because light requires time to travel. Telescopes do not simply magnify distant objects, they collect older light. A telescope aimed at a nearby star gathers light that left that star years ago. A telescope aimed at a distant galaxy gathers light that left billions of years ago. The instrument itself does not change time. It only intercepts light that has been travelling for a long while. This turns the universe into a layered archive. Nearby regions show recent conditions. Farther regions show earlier ones. There is no single cosmic moment on display. Instead, there is a continuous gradient of time extending outward in all directions. This archive is not organised by intention or design. It is a natural outcome of finite light speed. Space becomes a map of time because information cannot travel instantly. Distance is what separates moments. When astronomers compare objects at different distances, they are not just comparing locations, they are comparing stages of cosmic development. Younger galaxies appear smaller and less structured. Older galaxies appear more settled. These differences are not guesses. They are direct observations of light from different times. Light allows us to see how stars formed, how galaxies assembled, and how large-scale structures emerged. Each observation captures the universe in a different phase of its history, preserved by light's steady travel. This does not require the universe to remember itself. It simply continues emitting light. That light moves outward, carrying snapshots of changing conditions. The archive is created automatically, without storage or intention. The farther we look, the deeper into the past we see. At great distances, we observe galaxies as they were long before the Earth formed. At even greater distances, we approach eras when the universe itself was much younger and denser. There is no sharp boundary between these eras. The transition is smooth. Each additional unit of distance corresponds to an earlier slice of time. The universe unfolds gradually as observation reaches farther out. This perspective removes any sense of separation between space and history. They are not independent layers. They are aspects of the same structure, connected by light's finite speed. For the listener, there is no need to imagine vast timelines all at once. It is enough to recognize that the night sky contains many different moments, quietly coexisting as light in transit. Nothing about this archive is fragile. It does not decay simply because time passes elsewhere. Light remains reliable until it is absorbed or scattered. The past remains physically present as long as its light continues travelling. As we continue, we will move even closer to the earliest light the universe allows us to see. But for now, we can rest with this understanding. The universe does not hide its history. It carries it forward, continuously, through light. Some of the light reaching us today began its journey before many familiar structures existed. It has been travelling for billions of years, crossing expanding space while the universe around it changed dramatically. Yet the light itself remains a direct connection to those early moments. When a galaxy emits light, that light spreads outward in all directions. If the galaxy is far enough away, the light reaching us today left when the universe was much younger. Stars within that galaxy may have been forming for the first time. Chemical elements may have been simpler, structures may have been less organised. This ancient light does not carry labels telling us how old it is. Its age is inferred from distance and from how the universe has expanded during its journey. By measuring how much the light's wavelength has stretched, scientists determine how long it has been travelling. The stretching of light is not due to fatigue or loss. It occurs because space itself expands. As light moves through expanding space, the distance between successive wave crests increases. This shifts the light toward longer wavelengths. This process does not blur the information carried by the light. It alters the scale at which the information appears, but the underlying patterns remain readable. Spectral lines shift, but their relative positions are preserved. Because of this, ancient light remains useful. It allows scientists to identify elements, temperatures, and motions in very distant objects. Even after billions of years, the light carries clear signatures of its origin. The universe does not recycle this light. Once emitted, it continues outward until it interacts with matter. Much of it will never be detected. It will pass through space indefinitely, carrying early moments forward. From our perspective, detecting this light feels like receiving a message delayed by immense time. But from the universe's perspective, it is simply a continuous process. Emission happens, travel happens, detection may or may not happen. This long travel does not weaken light's role as a time messenger. On the contrary, it strengthens it. The longer light travels, the more separated the emission moment is from the detection moment, and the clearer the distinction between past and present becomes. Yet even at these scales, there is no break in continuity. The same rules apply. Light moves, time passes for observers, information arrives. It is not necessary to imagine light enduring hardship or effort during this journey. It does not struggle, it does not age. It simply follows the structure of space-time. As we consider ancient light, we are not peering into something abstract. We're intercepting radiation that has physically existed and moved through space since its emission. The past is not recreated. It is encountered directly. This understanding can remain calm. Ancient light does not demand interpretation beyond what it carries. It is a steady record, preserved by motion and distance. In the next step, we will consider the oldest light that can be observed at all, and what it tells us about the universe's earliest conditions. The oldest light we can observe does not come from stars or galaxies. It comes from a time before any of those structures existed. This light fills the universe uniformly and arrives from all directions with remarkable consistency. This radiation is known as the cosmic microwave background. It was emitted when the universe was very young, at a time when matter and radiation first became able to move freely through space. Before this moment, the universe was too dense and hot for light to travel far without constant interaction. When the universe cooled enough for atoms to form, light was released and began travelling outward in all directions. That light has been moving ever since. It has not been refreshed or replaced. What we detect today is the same radiation, stretched by the expansion of space. The cosmic microwave background does not show individual objects. It shows a nearly uniform glow with tiny variations in temperature. These variations reflect small differences in density in the early universe. Over time, those differences grew into the large-scale structures we see today. This light has been travelling for over 13 billion years. During that time, the universe expanded dramatically. The light's wavelength stretched from visible and infrared into the microwave range. Despite this stretching, the information encoded in the light remains intact. By studying this radiation, scientists gain a snapshot of the universe at a very early stage. It represents a boundary in time. We cannot see earlier than this using light because earlier light could not travel freely. This boundary is not imposed by technology, it is imposed by physics. Before the cosmic microwave background was emitted, the universe was opaque to light. Observation using light was not possible. The existence of this oldest observable light reinforces the idea that light defines what can be seen across time. There is a limit to how far back observation can reach, and that limit is set by the behaviour of light in the early universe. This does not suggest mystery or absence. It simply marks where light-based observation begins. Beyond that point, other methods may be required to infer conditions, but light itself cannot carry information from earlier times. The cosmic microwave background arrives steadily and quietly. It does not announce its age, it simply exists as a constant presence, a uniform glow that surrounds us. In this way, light carries not only local history but cosmic history. The universe reveals its early state not through memory, but through radiation still in motion. We can let this idea settle gently. There is an oldest light we can see. It continues to travel. It continues to arrive. It anchors our understanding of the universe's timeline without urgency or interpretation. As light travels across the universe, it does so through space that is not static. Space itself expands. This expansion does not push light in the way a force would. Instead, it gradually stretches the distances between points that light passes through. When space expands, the wavelength of light travelling through it stretches as well. Each wave crest becomes slightly farther from the next. This process is slow and continuous, and it affects all light that travels across large cosmic distances. This stretching is known as cosmological redshift. It does not occur because light loses energy in transit through time. It occurs because the space light moves through changes while the light is already on its way. As the wavelength increases, the light shifts toward the red end of the spectrum. Light that was once visible may arrive as infrared or microwave radiation. The information remains, but its scale changes. This effect allows observers to measure how much the universe has expanded during the light's journey. By comparing the observed wavelength to the wavelength emitted, scientists can infer how long the light has been travelling and how space has changed in that time. The expansion of space does not slow light locally. At every point along its path, light still moves at its constant speed relative to nearby space. The stretching happens to space itself, not to the motion of a light within that space. This distinction is important. Light does not age or weaken as it travels. It remains consistent at each moment along its path. The changes we observe arise from the evolving structure of the universe around it. Over very long distances, these small stretches accumulate. Light from distant galaxies arrives significantly redshifted, carrying clear evidence of cosmic expansion. The farther the source, the greater the shift. This process does not blur time, it refines our understanding of it. The amount of stretching tells us how much the universe has grown since the light was emitted. Distance becomes a measure not only of time passed, but of cosmic change. Light thus carries two kinds of temporal information. It tells us when it was emitted through its travel time. It also tells us how space evolved during that journey, through its stretched wavelength. These patterns are steady and predictable. They do not fluctuate randomly. The expansion of space proceeds smoothly on large scales, and light records that smoothness faithfully. There is no need to imagine light struggling against expansion. It is not resisted. It simply moves while space changes. The result is a gentle imprint of cosmic history encoded in the light itself. As we continue, we will consider the boundaries of what light can tell us, and where observation naturally comes to rest. For now, it is enough to recognize that time, space, and light remain linked even as the universe grows. There is a natural boundary to how far light can carry information to us. This boundary does not come from limits of vision or technology. It comes from the history of the universe itself and the way light interacts with matter. As we look farther into space, we look farther back in time. Eventually we reach an era when light could not travel freely. Before atoms formed, the universe was filled with charged particles that scattered light constantly. Photons could not move long distances without being absorbed or redirected. This means that light-based observation has a starting point. Beyond that point, earlier moments are not accessible through light alone. The universe was not dark. It was bright and hot, but it was opaque, not transparent. This limit is calm and well defined. It does not suggest hidden meaning or absence. It simply marks the earliest time at which light could begin its uninterrupted journey through space. From that moment onward, light has been travelling continuously. Every later event has contributed new waves of information, but nothing earlier could send light that reaches us today. This boundary reminds us that observation is always shaped by physical conditions. Light can only carry what it is allowed to carry. Where it cannot travel, it cannot inform. There is no frustration in this limit. It is a stable feature of the universe. It tells us where light's story begins, not where understanding ends. Light's relationship with time is not only cosmic, it also shapes how humans measure and coordinate time in practical ways. Our definitions of seconds, distances, and synchronization all rely on light's steady behavior. Modern timekeeping uses atomic clocks, which depend on precise electromagnetic transitions. These transitions involve light at specific frequencies. Because light's properties are stable, they provide a reliable foundation for measuring time. Distance, too, is defined using light. A meter is defined by how far light travels in a fixed fraction of a second. This ties space and time together directly, using light as the bridge. When clocks are separated by distance, light signals are used to synchronize them. The travel time of these signals must be accounted for. Without this correction, timekeeping would drift. In navigation systems, light's timing is essential. Signals sent from satellites arrive with predictable delays. By measuring these delays, positions are calculated. Light turns time into location. These uses are quiet and routine. They do not feel connected to cosmic history. Yet they rely on the same principles that govern light travelling across the universe. This continuity across scale reinforces the stability of physical law. Light behaves the same way whether crossing a laboratory or a galaxy cluster. Across all scales, patterns repeat. Light links time and space in atoms, in planetary systems, and in the largest cosmic structures. The details change, but the structure remains. Small systems show short delays, large systems show long ones. Motion and gravity adjust timing, but never break the connection. Light remains the constant reference. This consistency allows understanding to scale without strain. We do not need new rules for each level. The same behavior applies everywhere. By observing these repeating patterns, we see that the universe is not fragmented. It is continuous. Light provides the thread that connects its parts across time. These patterns do not demand interpretation. They simply exist. Observation follows them naturally. Within this steady flow, human observation takes place. We do not stand outside time or light. We receive what arrives when it arrives, shaped by distance and motion. Our position is not central or isolated. It is one point among many, receiving light from nearby and far away, recent and ancient. There is no need to assign importance or meaning to this position. It is enough to notice the continuity. Light arrives. Information connects. Time unfolds. Observation becomes a quiet participation in a larger process, not a separate act. Light continues to move. It leaves sources, travels through changing space, passes through gravity, and arrives after delays set by distance. This process does not conclude. It does not pause. Every moment sends light forward. Every observation receives light from behind. Time is not reversed or escaped. It is connected. Nothing needs to be gathered or resolved. The motion continues whether it is noticed or not. Everything flows. Sleep in that motion.